The scariest possibility is not that aliens will come one day, it is that they may already be on the way. And if that is true, then the real question is not if, but how close. But before we continue, please subscribe to the channel to give your support. Let's continue. The biggest mistake people make in this topic is assuming alien contact has to begin in the future. You usually think about aliens as something that shows up later, some event that happens after a signal, after a discovery, after some huge public moment. But that way of thinking is built around human timing, not cosmic timing. The universe is not working on your schedule. The Milky Way is about 13.6 billion years old. Earth is around 4.54 billion years old. Modern humans have existed for only about 300,000 years. And your technological phase, the period where humans can actually detect things across space and send radio into space, is only a little more than 100 years old. That is an extremely small slice of time. So if another civilization appeared even 10,000 years before us, it would already have a lead longer than all of recorded human history. If it appeared 1 million years before us, then in galactic terms, humans are not early at all. Humans are late. That one point changes the whole discussion. The question is not just whether aliens exist, the question is whether some civilization had enough time to begin a journey long before humans were ready to notice. Now here is the next problem. People always say the same thing. Space is too big. Interstellar travel takes too long, so aliens coming here does not make sense. The first part is true. Space is extremely big. The nearest star system, Alpha Centauri, is about 4.37 light-years away. That is roughly 41.3 trillion kilometers, or 25.7 trillion miles. Those numbers are so large that they sound like the end of the argument. But they are only the end of the argument if you think on human timescales. If a probe moved at 1% of the speed of light, about 3,000 kilometers per second, or about 1,864 miles per second, it could reach Alpha Centauri in a few centuries. For a human life, that is far too long. For a civilization planning across hundreds or thousands of years, it is not absurd at all. It is slow, but it is still workable. That is the first real shift you need to make. Distance is huge, but time is even bigger. And if a civilization is old enough, then long travel time stops being a reason to dismiss the idea. Then there's another assumption that also falls apart. You probably think first contact would begin with a signal, some message, some transmission, some clear attempt to communicate. But there is no rule that says that has to happen first. A civilization could launch probes before Earth was even detectable as a technological world. It could launch them before humans invented radio. It could launch them before humans existed at all. By the time people on Earth built telescopes, antennas, and space programs, something could already have been moving through interstellar space for centuries. That is the part that makes this topic much more serious than people first think. The trip does not need to start during your lifetime for the arrival to matter during your lifetime. A launch that happened hundreds or thousands of years ago could still produce an arrival much later. If the civilization that sent it thinks in long-term projects, then that delay is not a failure. It is just part of the mission. And this is not just science fiction logic. It follows from normal physics. We already know that objects can travel between stars. Interstellar objects have passed through our own solar system. Oumuamua and Borisov were natural objects, not alien machines, but they matter because they prove the route is real. Material from one star system can cross interstellar space and enter another star system. That means the path itself is physically possible. The question is not whether anything can move between stars. We already know that it can. The question is whether a technological civilization could do it on purpose. And based on known physics, the answer is yes. Not easily, not cheaply, and not quickly by human standards, but yes. If a civilization has enough energy, enough engineering ability, and enough patience, then sending something between stars is possible. It does not require faster than light travel. It does not require wormholes. It does not require breaking relativity. It only requires accepting that long travel time stops being a reason to dismiss the idea. That last point matters a lot because humans tend to judge every mission by whether it fits inside a human life. A more advanced civilization may not think like that at all. It may build projects meant to last centuries. It may send machines, not living crews. It may treat a 300-year trip the way modern states treat long-term infrastructure. If that is true, then one of the main reasons people dismiss alien travel is really just a human limitation, not a physical limitation. So now the argument becomes much sharper. For aliens to already be on their way to Earth, you do not need exotic physics. You only need a civilization older than ours, a mission launched long ago, and technology good enough to survive a long crossing. In a galaxy this old, that is not an absurd combination. It's a real possibility. And once you see that clearly, the old question stops being the most important one. Will aliens ever come here is too narrow. The more serious question is whether the journey could have already started long before humans were paying attention. Because if another civilization had a long head start, then humans would not be waiting at the beginning of the story. Humans would be entering it very late. And that leads directly to the next problem. Even if interstellar travel is possible, that still doesn't mean there were enough suitable worlds, enough opportunities, or enough time for civilizations to arise early enough to matter. But once you look at the number of planets in the galaxy, that comfort starts to disappear very fast. The next problem is even harder to ignore. Because once you ask where alien missions could come from, the answer may be almost everywhere. A few decades ago, people still had a fallback position. They could say maybe planets are rare, maybe Earth is unusual, maybe most stars are just empty systems with nothing going on around them. That argument does not work anymore. Modern astronomy has changed that completely. Missions like Kepler, along with many follow-up surveys, showed that planets are not some rare exception. They are normal. They are everywhere. The Milky Way likely contains hundreds of billions of planets. Many stars do not just have one world, they have multiple worlds. And that matters because every planet is a place where chemistry, climate, geology, and time can interact for millions or billions of years. Every planetary system is a long-running experiment. That is the first major change in the logic. You are no longer dealing with a galaxy that has only a few chances for life to appear. You are dealing with a galaxy filled with chances. And that immediately raises the next question. Are Earth-like worlds actually rare, or are they common too? That answer is also moving in the wrong direction, if you want the universe to stay empty. Rocky planets are not exotic. Earth-sized planets and super-Earths show up around many kinds of stars, around red dwarfs especially. Compact systems packed with planets seem to be very common. Not every one of those planets is friendly to life. Not everyone has the right temperature, the right atmosphere, or the right surface conditions. But once the total number gets large enough, even a small fraction turns into a huge absolute number. Depending on the model, the Milky Way may contain billions of potentially habitable rocky planets. And that phrase matters. Potentially habitable does not mean inhabited. It does not mean life is there. It does not mean intelligence is there. But it does remove the older idea that Earth has to be a one-time accident in a mostly barren galaxy. The galaxy clearly makes planets in large numbers. It clearly makes rocky planets in large numbers. It likely makes a very large number of worlds where liquid water could exist under the right conditions. So even before you prove that life is common, you already have to accept something important. The stage is not rare. The stage is everywhere. Now push that one step further, because this is where time starts to matter as much as planet count. The Sun is around 4.6 billion years old. That sounds ancient on human terms, but in galactic terms, it is not especially early. Many stars in the Milky Way formed long before the Sun did. Some planetary systems may be 1 billion years older than ours, some 2 billion, some 3 billion, some perhaps even 5 billion years older. That gap is so large that people usually say the numbers without really feeling what they mean. A civilization with a technological lead of 100,000 years over humanity would already be beyond anything you can realistically compare to modern society. A lead of 1 million years would be far beyond that. A lead of 10 million years moves the discussion out of normal historical thinking completely. A lead of hundreds of millions or billions of years is not just more advanced. It is operating on a scale where interstellar infrastructure, long-duration machine missions, and deep time planning stop sounding extreme. That is why the age structure of the galaxy matters so much. If intelligent life ever appeared on some older worlds, then those civilizations did not just get a small head start. They got a head start larger than the entire history of complex life on Earth. And that leads to the obvious objection. Habitability is complicated, so maybe most of those planets still don't matter. That part is true. Habitability is messy. It is not just about being the right distance from a star. You may need long-term climate stability. You may need enough water, but not too much. You may need plate tectonics, or maybe not, but some kind of long-term carbon cycling probably helps. You may need magnetic shielding, or at least enough atmospheric protection to reduce damage from radiation. You need chemistry that can persist. You need a world that does not keep sterilizing itself with impacts, runaway greenhouse effects, or long-term atmospheric collapse. So yes, the habitable zone by itself is not enough. A planet can sit in the right orbit and still be completely unfriendly to life. But this is exactly where scale becomes dangerous to the comforting argument. Once you have hundreds of billions of planets and possibly billions of rocky worlds in broadly favorable conditions, you don't need habitability to be easy. You don't even need it to be common. Even if only a tiny fraction of those worlds stay stable enough for life, and only a tiny fraction of those ever produce intelligence, and only a tiny fraction of those ever reach technology, you may still end up with many civilizations across cosmic history. The numbers don't prove aliens exist. They do something more limited, but still important. They take away the easy dismissal. You can't just wave the problem away by saying there were never enough places for it to happen. There were. And now the tension increases again, because once you combine large numbers of planets with large differences in age, the timeline gets uncomfortable very fast. A civilization that formed on a planet 1 billion years older than Earth would not need to be launching missions now. It could have started a very long time ago. It could have reached its machine age when Earth was only microbial life. It could have built telescopes and surveyed young planetary systems while our planet was still changing its atmosphere. It could have launched slow probes while Earth was still mostly a bacterial world. It could have marked the solar system as interesting before plants, before animals, before mammals, before humans. That changes the entire tone of the discussion. Aliens on their way stop sounding like a future event and start sounding like a consequence of deep time. If the galaxy has been producing planets for billions of years, and if some fraction of older worlds produced intelligence, then the launch window for interstellar missions may have opened long before Earth even had complex life. And that's the point that really matters here. You don't need to assume aliens detected modern civilization and then rushed towards us. They may not have come because of cities, satellites, or radio. They may have targeted Earth because it was habitable, or because it was alive, or because it was simply on a list of chemically interesting worlds orbiting stable stars. In that case, the mission timeline could be vastly older than human history. So the old comfort disappears again. It is not enough to say maybe they haven't had time. In a galaxy this old, many systems had enormous amounts of time. It is not enough to say maybe there weren't enough worlds. There are too many worlds for that excuse to hold. And it is not enough to say maybe Earth is too special. Modern exoplanet science is moving in the opposite direction. Earth may still be rare in the exact details, but planets themselves are common. Rocky planets are common, and opportunities for life may have existed on a huge scale, which means the next question becomes even more serious. Even if the galaxy had enough worlds, and enough time, and enough older systems, interstellar travel is still brutally difficult. So does that finally stop the idea, or does difficult still fall short of impossible? Interstellar travel is hard, But hard is not the same as impossible, and that distinction changes everything. A lot of people reject this whole idea for the wrong reason. They picture alien travel in the most extreme form first: huge crewed ships, instant arrival, violent acceleration, something that looks cinematic and impossible. Then they say that can't happen, so the whole subject collapses. But that logic fails because it chooses the hardest version of the problem and treats it like the only version that counts. Real physics gives you more options than that. You don't need faster than light travel. You don't need to break relativity. You don't need a giant living city crossing the galaxy. You can do interstellar travel with robotic probes, generation ships, fusion-powered concepts, beamed sails, or slow autonomous machines that just keep going for centuries. None of that is easy, but none of it requires magic. That's the first correction. The question is not whether alien travel looks easy by human standards. The question is whether known physics allows it at all. And the answer is yes. Now, the next issue is speed, because this is where the problem becomes brutally real. Chemical rockets, the kind humans actually use, are far too slow for practical interstellar missions. Voyager 1 is moving at roughly 17 kilometers per second relative to the Sun, about 38,000 miles per hour. That sounds extremely fast until you compare it to the distance between stars. At that speed, reaching Alpha Centauri would take on the order of tens of thousands of years. So if your standard is current human rocket technology, then yes, interstellar travel looks hopeless. But that is not the right comparison. The real comparison is between different fractions of light speed. At 1% of light speed, about 3,000 kilometers per second, or 1,864 miles per second, the trip to Alpha Centauri drops from tens of thousands of years to a few centuries. At 10% of light speed, around 30,000 kilometers per second, or about 18,600 miles per second, now you are talking about a trip that can happen on the scale of decades, at least if you simplify the acceleration and deceleration problem. That is still an extreme engineering challenge, but it is no longer in the category of fantasy. It moves into the category of energy, materials, shielding, and mission design. And that is the point most people miss. The speed problem is brutal, but it is measurable. Once a problem becomes measurable, it stops being pure impossibility and becomes engineering. So then the obvious question is, has anyone actually studied this seriously, or is this just speculation? The answer is yes, it has been studied seriously. Humanity has not built an interstellar craft, but scientists and engineers have examined real concepts for decades. In the 1970s, Project Daedalus looked at an uncrewed fusion-powered probe designed to reach another star. More recently, Breakthrough Starshot proposed tiny light sail probes pushed by powerful lasers to around 20% of light speed, roughly 60,000 kilometers per second, or about 37,000 miles per second. That proposal is still theoretical, and the technical barriers are enormous. You would need extreme beam control, highly advanced sail materials, accurate targeting, protection from dust impacts, and some way to send useful data home after the flyby. But the important point is not whether humans can do it tomorrow. The important point is that respected researchers can design missions that stay inside known physics. Once a design exists in principle, you lose the right to dismiss the whole category as science fiction. Now here's the next mistake people make. They keep picturing aliens as biological passengers. They imagine life support, food, comfort, gravity, air, sleep cycles, families, and all the other things humans would need on a long voyage. But that may be completely wrong. The first thing crossing interstellar space is much more likely to be a machine than a crew. A robotic payload does not get bored. It does not need windows. It does not care if the trip takes 200 years or 500 years. It can hibernate. It can wake only when needed. It can run diagnostics, repair systems, and stay quiet for most of the journey. If the machine carries advanced AI, then it may not just be a tool. It may be the mission itself. That changes the time problem immediately. For a biological crew, a 500-year journey is a civilization-defining challenge. For a machine, it may just be the schedule. And if a civilization values knowledge, survival, exploration, or backup options for its species, then slow robotic missions start to make strategic sense. They may even be the smartest option because they reduce mass, reduce life support complexity, and make long travel times far less important. Then there's another objection. Interstellar space is dangerous, and that part is completely true. The space between stars is not empty in the simple way people imagine. There's gas, dust, radiation, magnetic fields, and high-energy particles. At high speed, even something tiny becomes dangerous. A grain of dust hitting a spacecraft at 10% of light speed carries enormous kinetic energy. Enough small impacts could destroy exposed systems. Radiation can damage electronics. Long-duration missions face cumulative degradation. So yes, interstellar space is hostile. But hostile is still not the same thing as closed. These are design problems. You can think about sacrificial forward shields, multiple shield layers, dust detection systems, magnetic deflection for charged particles, hardened electronics, distributed systems, and redundancy. None of those ideas make the mission easy, but they do show the same pattern again. The road is dangerous, not forbidden. Natural interstellar objects already cross between star systems. That proves the path itself is real. A technological civilization would not be fighting a non-existent route. It would be trying to survive a known route better than a rock or a comet can. And that brings you to the most important conclusion in this section. Once you remove the Hollywood version of the problem, interstellar travel changes category. It stops being impossible and becomes expensive, slow, and large-scale. That still sounds severe, but it is enough for this argument, because you do not need every civilization in the galaxy to do it. You don't need millions of alien empires launching fleets every year. You only need one civilization once, somewhere in the Milky Way, at some point in billions of years, to decide that sending something outward is worth the cost. That is a much lower bar than people usually assume. And if even one civilization ever crossed that bar, then the galaxy may already contain missions still in transit right now. Old missions, slow missions, machine missions, missions whose makers may be gone, changed, or unrecognizable by the time the craft reaches its destination. The launch could be ancient history, and the mission could still be active. So now the tension gets worse again, because once you accept that probes are more realistic than giant empires or giant ships, the old comfort of the Fermi Paradox starts to weaken. If aliens are not required to show up as obvious galaxy-wide conquerors, then where is everybody may not be as reassuring as it sounds. The Fermi Paradox sounds comforting only if you assume aliens should be loud, visible, and easy to recognize. It assumes the natural end state of intelligence is something huge and obvious, but there is no reason that has to be true. Maybe the galaxy is not full of giant empires at all. Maybe it's full of quiet machines, small survey craft, dormant systems, and passive observers. If that is the real pattern, then the absence of giant monuments doesn't protect you. That's the first shift. Where is everybody may be the wrong question. The better question may be, what if most of them were never trying to be seen in the first place? And once you ask that, the logic gets more serious very fast, because exploration scales much better than colonization. If a civilization wants information about thousands of star systems, it does not need billions of living beings. It does not need giant colony fleets. It does not need to build a dramatic empire everywhere it goes. It can just launch probes. Machines are lighter, cheaper, easier to replicate, and much easier to keep functional over long durations than living populations. Humanity is already doing the first crude version of this. When humans want to study Mars, the outer planets, asteroids, or distant environments, the first choice is almost always robotic. Rovers, orbiters, flyby probes, landers, telescopes, sample-return missions. That's already the pattern. The more capable a civilization becomes, the more likely its first interstellar presence is not a giant ark full of passengers, but a distributed network of instruments. That matters because it means the galaxy could contain a lot of alien activity without looking anything like a science fiction empire. Now, take that one step further. What if one civilization did not just send a few probes, but built a system that keeps spreading? This is where the idea of self-replicating probes enters the picture. The basic concept is simple. A civilization sends autonomous probes to nearby star systems. Once a probe arrives, it uses local material, maybe asteroids, maybe small moons, maybe other accessible resources, to build copies of itself or simpler follow-up machines. Those then travel onward to other systems. This is the classic von Neumann probe concept. It sounds extreme at first, but the underlying logic is straightforward. If replication is possible, then exploration no longer depends only on the industrial output of the original home world. The network expands itself. And here is why that matters for the Fermi Paradox. Even if those probes move slowly, even at modest interstellar speeds, a self-replicating wave could in principle spread across the galaxy in millions of years. That sounds like a huge amount of time to you, but compared to the age of the Milky Way, it is actually short. The galaxy is more than 13 billion years old. So if replication is feasible at all, and if even one civilization started such a process long ago, then silence becomes much harder to explain. That does not prove it happened, but it makes the absence of obvious empires much less useful as a comforting argument. Then there's the question of signals, because a lot of people still rely on the idea that if aliens were out there, SETI would have heard something by now. But that assumes a lot. SETI has searched for radio signals for decades, and that work is scientifically important, but the search volume is still tiny compared with the full parameter space that exists. There are many possible frequencies, many possible signal types, many possible modulation methods, many possible directions, many possible time windows, and many possible communication strategies. A civilization may not use radio much. Its transmissions may be narrow, intermittent, encrypted, extremely brief, or directed somewhere else entirely. It may communicate in ways humans are not monitoring, or it may choose not to broadcast at all. And the probe-based strategy avoids that whole problem. If your goal is to learn about another system, you do not need to announce yourself across light years. You can just send something there. Physical presence does not require loud signals, so silence in radio data does not mean there is no activity. It may only mean you're listening for the wrong kind of evidence. That is where the paradox stops being reassuring and starts becoming more unsettling, because now the question changes. It is no longer, why is there no giant alien government in the sky? That was always the easier version of the question. The harder version is, why have we not conclusively found artifacts yet? And that is much less comforting, because artifact searches are still primitive. Humans have not exhaustively searched the moon for anomalous objects. Humans have not exhaustively searched Mars for non-natural relics. Humans have not fully surveyed the Earth-Sun Lagrange points, where objects can remain in useful gravitational positions for long periods. Humans have not completely searched the asteroid belt for strange bodies with suspicious spectra, unusual thermal behavior, or impossible-looking geometry. Humans have not fully characterized every interstellar object entering the solar system, and certainly have not ruled out every non-natural possibility in those trajectories. That is the critical point. You cannot honestly say there is nothing there when the search has barely begun. This is where the Fermi Paradox changes meaning. In the Empire version, silence looks like evidence against alien presence. In the probe version, silence may just reflect weak search methods. If advanced civilizations prefer quiet machines over giant expansion, then the absence of huge signs does not tell you much. It may only tell you that you are not very good at finding subtle things yet. And subtle things are exactly what you should expect. A smart probe would not need to be large. It would not need to be bright. It would not need to sit in a place humans constantly monitor. It could hide in orbital clutter. It could remain dormant. It could operate passively. It could be designed to avoid drawing attention unless it needed to act. In that case, the absence of obvious evidence is not surprising at all. So the paradox does not go away, but it does become sharper. If probes are easier than empires, cheaper than colonization, quieter than broadcasting, and potentially able to spread over long timescales, then where is everybody stops sounding like a dismissive argument. It becomes a more disturbing puzzle. Not because the evidence is stronger than it is, but because the old comfort was based on the wrong expectation. And that naturally leads to the next question. If the most realistic first visitors are not giant crews or empire builders, then what would they actually be? The answer is probably much colder, much smaller, and much less human than most people expect. The most realistic first visitors would probably not be living aliens at all. They would be machines. A lot of people still picture interstellar travel the wrong way. They imagine biological beings sitting inside a ship, staying alive the whole time, eating, sleeping, aging, dealing with radiation, and somehow surviving a trip that could take centuries. That's the human version of the problem, but there is no reason to think that's the version an advanced civilization would choose. Biology is fragile. Living organisms need stable temperatures, air, water, food, waste recycling, shielding from radiation, and protection from long-term system failure. Interstellar space is extremely hostile to all of that. Cosmic rays are a constant problem. Micrometeoroids are dangerous. Vacuum is absolute, and long mission times make every biological requirement harder. A machine does not have those limits in the same way. It can sit in darkness, powered down, for hundreds or thousands of years if it's built for that purpose. That's the first reason machines are the better answer. They remove most of the hardest parts of the mission. Then there's the mass problem, and this one is just physics. Accelerating mass is expensive. The more mass you try to push to high speed, the more energy you need, and the burden rises fast. That's bad news for giant crewed ships and much better news for small robotic payloads. A lightweight machine is simply easier to launch, easier to accelerate, easier to shield, and easier to keep functional over long timescales. That's not just a guess about alien logic. Even human thinking already moves in that direction. When scientists discuss realistic interstellar concepts, they often focus on tiny probes, autonomous scouts, or very tightly optimized machine systems. The reason is simple. Physics pushes you there. If the destination is another star, the first thing across the gap is much more likely to be something compact, hardened, and efficient, not a flying city. And once you accept that, the next point gets even more serious. A machine may not just be carrying intelligence, it may be the intelligence. For humans, there is still a strong emotional divide between a robot and a person, but a more advanced civilization may not think that way at all. If intelligence can exist in machine systems, then sending a robotic craft may be equivalent to sending a mind, or part of a mind, or a digital individual, or a whole archive of personalities and knowledge with the ability to act on its own. From that perspective, interstellar travel changes completely. You do not need to keep a biological body alive for centuries if cognition itself can be embodied in durable hardware. You do not need a living passenger if the machine is already the passenger. That possibility matters because it lowers the barrier even further. A civilization might solve long-distance travel the moment it solves portable intelligence. At that point, probe and visitor may start to mean the same thing. And this should not sound as strange as it first does, because humans already trust machines to do science far away from home. The Voyager probes are still operating beyond the outer planets. Mars rovers make navigation choices on their own within defined limits. Space telescopes carry out very complex observing programs. Autonomous systems are already the first line of exploration. Human space science has already accepted the basic idea that machines go first because machines handle distance and danger better. Right now, our autonomy is still primitive, but even this primitive version is enough to show the direction. Extend that line forward by a few thousand years, and self-directing, self-maintaining interstellar explorers stop sounding exotic. They start sounding like the obvious choice. That brings the whole argument to a much darker possibility, because a machine does not need to arrive in any dramatic way. It does not need to descend into Earth's atmosphere. It does not need to send a message. It does not need to make itself visible. A machine could enter the solar system, slow down or adjust trajectory, settle into a stable orbit, hide among asteroids, park near a useful gravitational point, and simply watch. It could use passive sensors. It could minimize emissions. It could wait for years, decades, or longer before doing anything noticeable. That idea is one reason some scientists have discussed the possibility of lurkers, hypothetical extraterrestrial probes that might observe without revealing themselves. There is no confirmed evidence that such objects exist. That part has to stay clear. But the concept itself is physically reasonable. And once you admit that point, the meaning of contact changes. Contact does not have to mean communication. Contact does not have to mean landing. Contact does not have to be in a public event that everyone recognizes at once. If the first visitor is a machine, then contact may begin as observation. It may begin as surveillance. It may begin as data collection carried out by something that never announces itself. That is why the machine scenario is so important. It is not just more realistic than living crews, it is also much harder to notice. A biological expedition is a huge commitment. It likely has to be large, resource-heavy, and operationally obvious. A machine mission can be much smaller and quieter. It can be specialized. It can be disposable. It can operate in stages. One machine might only be there to observe. Another might relay data. Another might wake only if certain conditions are met. A dormant probe does not need constant activity. It just needs enough durability to wait. And that waiting ability makes the whole idea more unsettling, because now the question is no longer only whether something could be traveling toward Earth right now. The question becomes whether something could already be here, inactive or hidden, without humans having recognized it yet. That is a very different level of tension. It moves the idea out of distant speculation and puts the focus on where such a system might actually stay if it entered our neighborhood quietly. And once you ask that, the next question becomes unavoidable. If a probe wanted to hide inside the solar system for a very long time, where exactly would it go? Not every alien arrival would end at Earth, and that makes the search much harder. If you were sending a survey probe into another solar system, diving straight into a planet's atmosphere would be a terrible plan. It's risky, it's loud, and it gives you very little room to observe safely. The smarter option would be to enter the solar system quietly and stay somewhere stable, or at least somewhere that does not require much energy to maintain position. That could mean a Lagrange point, an asteroid population, a high orbit around the sun, or even a co-orbital path that keeps the object moving with a planet without actually landing on it. So the first important point is simple. If something came here to watch, map, or wait, Earth itself would not have to be the destination. The solar system gives it a lot of better options. That leads directly to the next question. Where exactly could something stay for a long time without drawing much attention? One of the best answers is the Lagrange points. In a system with two large bodies, like the Earth and the Sun, there are special locations where gravity and orbital motion combine in useful ways. These are called Lagrange points. They're not magic hiding spots, and they're not fully stable in every case, but they can be very practical places to put a spacecraft. Humans already use them. The James Webb Telescope operates near the Sun-Earth L2 region because it gives a good observing position with manageable station keeping. If humans see these places as strategically useful, an advanced probe would see the same thing. A surveillance system placed in one of these regions could get broad lines of sight, long-term access to Earth and the inner solar system, and a position that makes operational sense without being obviously suspicious. And that's just one category of hiding place. The solar system also contains huge populations of small bodies, and those are even more useful if concealment matters. Jupiter has massive Trojan swarms, large groups of objects that share its orbit around the Sun. The Earth itself has a small number of known co-orbital companions and quasi-satellites. The asteroid belt contains millions of objects, and that's only one part of the picture. If a probe wanted to blend in, these environments provide natural clutter. A dark object with an irregular shape, low heat output, and no obvious emissions could be very difficult to distinguish from ordinary rocky bodies unless astronomers were specifically checking for unusual behavior. That means looking for strange orbital changes, unusual spectra, unexpected heat signatures, or geometry that looks engineered instead of natural. Without that kind of targeted search, an artificial object could easily be treated as just another minor body. That's the critical point. The solar system is not a clean, empty place where anything artificial would stand out immediately. It's crowded, complex, and full of background objects. Now, this is where the scientific caution matters because you don't want to jump from there are places to hide to there's definitely something hiding there. That would go beyond the evidence. But the opposite mistake is just as bad. You also can't say with confidence that there's nothing there because the relevant search has not been completed. The solar system is enormous. Neptune orbits at about 30 astronomical units from the Sun, roughly 4.5 billion kilometers, or about 2.8 billion miles. And that's still nowhere near the edge of the Sun's wider domain. Beyond the planets, the Oort cloud may extend tens of thousands of astronomical units. Even the inner solar system contains far more objects than humans have characterized in detail. We have discovered many asteroids and small bodies, but discovery is not the same as deep characterization. In many cases, astronomers know an orbit, a rough brightness, maybe some limited physical data, and that's all. So when people say, surely we would have seen it by now, that statement depends on a level of coverage we simply don't have. Absence of evidence here is strongly shaped by limited observation. That doesn't prove anything is there, but it absolutely weakens any claim that the local environment has already been ruled out. And that connects to a broader change happening in the science itself. SETI is no longer only about listening for radio signals. The field has widened to technosignatures, which means looking for signs of technology in many forms. That can include waste heats, strange atmospheric chemistry, engineered light patterns, non-natural orbital behavior, and physical artifacts. In other words, the search is expanding from is anyone transmitting to has anything technological left a trace? Once you frame it that way, local artifacts become a serious part of the discussion. Some researchers have argued that it makes sense to search near Earth space, the moon, stable orbital regions, and other strategic locations for non-natural objects. No verified alien artifact has been found. That has to stay clear. But the important point is that this is no longer just a fringe idea with no scientific structure behind it. There is now a real framework for asking the question in a disciplined way. And that should raise attention again, because now the idea is no longer just that aliens could be out there somewhere. The idea is that if a probe entered the solar system quietly, there are physically sensible places where it could remain for very long periods, and humans have not yet searched all of those places in anything like a complete way. So the picture gets more specific. A probe would not need to rush in. It would not need to announce itself. It could hide in clutter, sit in a useful orbit, stay cold, and observe. And if that sounds too speculative, the next section makes the problem even more concrete because we already know that material from other star systems can enter our solar system. That is not theory anymore. It has already happened. Interstellar objects are real, and that fact matters much more than most people realize. For a long time, interstellar visitors were basically a theoretical idea. Astronomers knew they should exist, but there was no confirmed example moving through the solar system. Then, that changed. In 2017, astronomers detected 1I, Oumuamua, the first confirmed interstellar object ever seen passing through our system. Then, in 2019, came 2I, Borisov, another confirmed interstellar visitor, this one much more clearly comet-like. Those two detections established something very important. Material from other star systems does not just exist somewhere far away in theory. It can actually pass through our neighborhood. The solar system is not sealed off. It is not isolated. Things from outside can come in. That point may sound simple, but it removes a major psychological barrier. Before those discoveries, it was easier to treat interstellar passage as something abstract. After them, you cannot do that anymore. The route is real. Now, the obvious response is fine, but we have only seen a couple of these objects, so maybe they are incredibly rare. But that conclusion does not follow. Detecting interstellar objects is hard. They are small, dim, fast, and often discovered late. By the time one is noticed, it may already be on its way out. It may only stay bright enough for good observations for a short period. So the fact that humans have only confirmed a small number does not mean only a small number exist. It mostly tells you that our detection systems are limited. And those systems are improving. Survey telescopes are getting better, sky coverage is expanding, and observatories designed to catch transients and moving objects will likely raise the discovery rate a lot. That means the solar system may be seeing more interstellar traffic than people intuitively think. Most of it is probably natural debris. Comets, fragments, icy bodies, rocky bodies. But the important thing is that the traffic lane itself is real. There is already movement through it. That's where Oumuamua becomes especially important, because it did not just get detected, it triggered serious debate. Oumuamua stood out because some of its observed properties looked unusual. Its brightness changed a lot, which suggested an odd shape or an unusual rotation state. It also showed a small non-gravitational acceleration, meaning its path was changing in a way that gravity alone did not fully explain. In a normal comet, you often expect outgassing, gas and dust escaping and acting like weak thrust, and you usually see some visible sign of that activity, like a coma. Oumuamua did not show the obvious dusty features people expected. That gap is what drew so much attention. Most researchers still favor natural explanations. Those include outgassing of materials that were hard to detect, unusual geometry, odd rotation, or exotic ice compositions. A smaller group raised the possibility of artificiality, but there is no strong evidence that Oumuamua was technological, and it's important to stay clear about that. The real reason Oumuamua matters is not that it proved alien technology. It didn't. It matters because it forced scientists to confront a new question in a serious way. If an artificial interstellar object passed through our data, what would it actually look like? That's a very different question from just asking whether aliens exist. It's a question about observation, about anomaly detection, about what kinds of signatures would make an object stand out from normal natural populations. And that leads to the deeper point. You don't need Oumuamua itself to be artificial for it to matter to this argument. Its real importance is that nature demonstrated the route for you. An object can enter from interstellar space, pass through the solar system, swing around the sun, and continue onward. That is no longer a hypothetical corridor. It is an observed one. Nature already ran the test case. Once nature proves the path exists, artificial entry becomes much more credible. Not proven, but more credible, because now the problem is no longer whether the solar system can be reached from outside. It clearly can. The problem becomes whether any civilization ever had the intent and capability to do it deliberately. That is a major shift. The route is no longer the weak point in the argument. The weak point is only whether anyone used it on purpose. And the next stage of this gets even more serious, because future detections may be far more informative than the first ones were. As surveys improve, astronomers should be able to detect interstellar visitors earlier, track them longer, and study them more carefully. That means better spectroscopy, better orbit reconstruction, better estimates of size, reflectivity, spin, and non-gravitational effects. Once you move from one or two examples to a real sample, strange behavior becomes easier to evaluate. And that's the key. You don't need one dramatic event where a giant alien craft stops over Earth. You just need enough data to identify something that clearly does not fit natural expectations. If even one interstellar object eventually behaves in a way that survives every natural explanation, then the implications would be enormous. So this section pushes the idea forward in a very direct way. The solar system is not isolated. Interstellar visitors can enter it. We have already confirmed that. We're probably missing many more than we catch. And as our observations improve, the difference between natural and non-natural objects may become easier to test, not harder. Which leads to the next uncomfortable step. If interstellar pathways are real, and if habitable worlds can be detected from far away, then a civilization looking outward may not need Earth to find it first. It may have been able to identify Earth as a target long before humans knew who or what was out there. If another civilization wanted to reach Earth, there's a very good chance it would have found Earth long before humans found it. People often talk about alien contact as if humanity is the side doing the searching, as if Earth is hidden until humans build better telescopes and start scanning the sky. But that assumes Earth was hard to notice. It was not. Long before humans built radios, rockets, and observatories, Earth was already giving itself away as a living planet. Our atmosphere has long contained chemical combinations that are difficult to maintain without biology. Oxygen is the biggest example. Methane matters too. When gases like these exist together over long timescales, they can point to active processes that are hard to explain with simple geology alone. That means Earth may have looked biologically unusual from very far away for a very long time.
So the first important point is this. Earth did not need humanity to become interesting. It was already interesting as a biosphere. That leads to the next question. Could another civilization actually detect that from a distance? Humans already use one of the key methods ourselves. When a planet passes in front of its star, a tiny fraction of the star's light moves through the planet's atmosphere before reaching a telescope. That light can carry information about gases in the atmosphere. This is one of the ways astronomers study exoplanets now. Human instruments are still limited, but the principle works. A civilization with more advanced telescopes, larger collecting areas, and longer observing time could do this much better than we can. Earth does not transit the sun from every direction in the galaxy, only from certain viewing angles. But from those directions, Earth becomes detectable in exactly this way. And that matters because it means Earth may have been visible as a living planet from specific regions of space long before humans had the technology to notice anything similar in return. Now push that one step further. A civilization that can detect life might also be able to detect technology. Humans are already thinking in that direction. Scientists have discussed whether future telescopes could detect industrial pollutants, artificial atmospheric compounds, unusual heat patterns, or even signs of large-scale energy use on exoplanets. Humans are not good at this yet, but the logic is straightforward. If certain chemicals are very hard to explain through natural processes, then they may act as markers of industry. If night side light becomes strong enough, that could become another clue. If a planet's heat distribution stops looking natural, that can matter too. So if humans are already considering these ideas at this early stage, then a civilization that is older and more advanced may have crossed that threshold a long time ago. That changes the timeline again. Earth may have first been detectable as alive and only later detectable as technological. And that brings in the modern phase. For roughly the last century, Earth has also been leaking radio and radar into space. People sometimes oversimplify this into a giant expanding radio bubble, but the reality is more complicated. Signal strength drops with distance. Not all transmissions are equally detectable. Some are directional, some are weak, some blend into noise quickly. So it is not as simple as saying the whole galaxy can hear Earth, but the broader point still stands. Over time, Earth became easier to notice, first as a biosphere, then potentially as a technological world. That means a civilization may not have needed to discover humanity from scratch. It may have already known Earth was biologically interesting and then later noticed that something new had appeared on the surface, technology. And now the time lag becomes important again. If such a civilization was in a nearby system and recognized that change a few centuries ago, then even a slow response mission could still be on the way now. It would not need faster than light travel. It would not need real-time coordination. It would only need enough interest in Earth and enough patience to launch something long before humans expected any reply. This is where the asymmetry becomes hard to ignore. Humans are often taught to think of themselves as the observers, the searchers, the ones trying to find life elsewhere. But in many realistic scenarios, Earth would have been the easier target. It is a water-rich world around a stable G-type star. It has a chemically active atmosphere. It has long-term surface liquid water. It has had strong biosignatures for immense spans of time. And more recently, it may also carry signs of industry and technology. In other words, if another civilization had better telescopes, more time, and a head start, Earth could have been cataloged as a high-interest planet long ago. That point changes the emotional direction of the whole story. Instead of asking when humans will finally detect someone else, you have to consider that someone else may have had a much easier time detecting Earth first. And if they did, then a mission aimed at this system would not need to wait for an invitation, a greeting, or a message from us. It could have started simply because Earth was a rare and valuable target. Maybe because it was alive. Maybe because it became technological. Maybe because it was both. And once you accept that, the next question gets even more serious. If a real mission were sent toward Earth, what would it actually look like in practice? It probably wouldn't be fast, flashy, or reckless. Physics would push it towards something slower, more automated, and planned on timescales much longer than human history. A real alien mission would probably not be built around speed. It would be built around patience. People naturally focus on fast travel because speed feels impressive and urgent. But once you look at the physics, speed becomes expensive very quickly. The energy needed to accelerate a spacecraft rises dramatically as velocity goes up. Push even a modest payload to 10% of light speed, and the power requirement becomes enormous. Not impossible, but enormous. You're no longer talking about the scale of a rocket launch in 1 century. You're talking about the kind of energy budget only a very advanced civilization could seriously manage. So, if a civilization is rational and willing to think over long spans of time, it may not choose the fastest mission. It may choose the most reliable one. Slower trajectories reduce stress, reduce energy cost, and may also make a craft easier to protect and harder to notice. That's the first thing physics pushes you toward, not dramatic speed, but careful optimization. Then there's a second point that matters just as much. Once a spacecraft has been accelerated, interstellar space offers almost no drag. There's no thick medium to slow it down every day the way air slows something down on Earth. That means coasting is extremely powerful. A mission can spend a large amount of energy at the beginning, then simply continue forward for centuries. From a mechanical point of view, that's very efficient. Launch once, coast for a very long time, arrive much later. And that changes the way you think about mission timelines. Humans are used to projects that last years, maybe decades if they're very large. But a civilization operating on deeper timescales could design missions that outlast governments, cultures, even species-level changes. The craft becomes its own long-term process. It doesn't need daily attention from home. It doesn't need the original launch civilization to remain unchanged. It just needs to keep functioning. In that sense, a probe can become a time capsule with a destination. That makes the whole concept much more realistic. The mission does not have to fit inside one lifetime or one era to still make sense. And that naturally leads to the next point. A realistic interstellar mission may not be one heroic journey from one homeworld straight to Earth. It may happen in stages. A more plausible model is something distributed. First, a civilization sends probes to nearby systems. Some of those systems provide resources. Then local infrastructure gets built, maybe automatically, maybe through machine industry, maybe through very slow expansion. From there, new probes are launched outward again. In that kind of network, not every mission has to begin at the original home planet. The burden gets spread out. The system extends itself step by step. That matters because it lowers the difficulty of reaching distant targets. By the time one probe is on the way to the solar system, it may not be a direct expedition from the civilization's birthplace at all. It could be the product of several stages of expansion or automated industry. And by that point, the civilization that began the whole process may have changed completely. It may have evolved, transformed, split, merged with machines, or disappeared. The mission still continues because the infrastructure and logic outlast the original society. That is a very different model from the way people usually picture alien contact. It is not one dramatic launch. It is a long chain of processes that keeps moving even if the original senders are no longer recognizable. Then there is motive, because people often assume the reason for interstellar travel would have to be conquest or pure curiosity. But there is another motive that may be even stronger: survival. A civilization that understands long-term risk has a strong reason to spread out. Planets are vulnerable. Stars change over time. Civilizations can destroy themselves. Impacts happen. Climate changes. Resources shift. Even without any enemy, a species that stays in one place forever accepts a single point of failure. Sending probes, archives, machine industries, or seed systems into other star systems creates redundancy. It gives a civilization more than one location, more than one chance, more than one future. That means interstellar missions may not be ambitious in a theatrical sense. They may simply be rational. Even if only one mission in 1,000 succeeds, that could still be worth doing if the alternative is eventual extinction. In that framework, sending probes toward habitable systems is not a fantasy project. It is long-term insurance. And once you see that clearly, the final point in this section becomes much more unsettling. A mission sent toward Earth may not have been sent because of humans at all. This is where the timeline becomes uncomfortable again.
If another civilization identified Earth as habitable or biologically active a very long time ago, then the launch could easily predate Homo sapiens. It could predate agriculture. It could predate mammals. The mission objective may have been environmental study, biosphere sampling, mapping, surveillance, or simple cataloging of an interesting living world. In that case, humans are not the reason for the mission. Humans are just what happened to be here by the time it arrived. That is a major shift in perspective. People usually ask, would aliens come for us? But the more realistic question may be, would they come for Earth? A water-rich, biologically active planet may be valuable even before it produces a technological species. If a probe was sent because Earth was alive, then the mission timeline may be vastly older than human civilization. We might be treating it as a response to us when in reality we were never the original target. That possibility is much colder and much more plausible than the usual version. It means the mission does not need to be reactive. It does not need to care what humans are doing right now. It may simply be finishing a process that started in deep time. So the logic keeps tightening. Fast travel is costly, so patience makes more sense. Long coasting is efficient, so century-scale missions are workable. Staged networks are more plausible than one-off voyages. Survival can be a stronger motive than curiosity, and the mission may be aimed at Earth as a habitable world, not at humanity as a special civilization. That gives you a much more realistic picture of what an inbound alien mission would look like. It would probably be slow, automated, resilient, and planned on timescales far beyond normal human thinking. And that points directly to the next problem. If humanity has mostly been listening for signals, but a real mission would likely be physical and quiet, then maybe we have been aiming our search in the wrong direction from the start. SETI has mostly been listening for signals, but that may be only one small part of the real search. Traditional SETI made a lot of sense when it began. Radio can travel huge distances. Humans discovered radio early in their technological history. And if another civilization wanted to make contact across interstellar space, a signal seems like the most obvious method. So for decades, the basic idea was simple. Listen carefully, scan the sky, and look for something artificial in the noise. That approach is still important, but it is also narrow by design. It assumes someone is transmitting. It assumes someone is transmitting strongly enough to be noticed. It assumes the signal lasts long enough. It assumes humans are listening at the right place, at the right frequency, at the right time. That is a lot of assumptions stacked on top of each other. A physical artifact does not have that problem. It does not need to stay synchronized with your listening window. It does not need to keep broadcasting for thousands of years. It can simply remain there, silent. That is why the search has started to broaden. Modern technosignature research is no longer just about radio signals. Scientists now talk about many different ways technology might show up in data. That includes waste heat from large-scale energy use, laser emissions, industrial chemicals in planetary atmospheres, strange transit patterns that could point to artificial structures, unusual dimming of stars, and possible artifacts inside our own solar system. None of this means alien technology has been confirmed. It has not. The important shift is that the field now accepts a wider range of possibilities. Intelligence may leave many kinds of signatures, not just messages. And that makes the whole topic more realistic, but also more unsettling. Because once you stop assuming aliens have to speak first, you realize they might be easier to detect through what they leave behind than through what they say. That idea is not strange at all when you compare it to archaeology. In archaeology, you often learn about a civilization from its ruins, tools, roads, or debris, not from hearing it speak directly. The same logic may apply at cosmic scale. A radio source can go silent, a civilization can disappear, a transmitter can fail, but an object in a stable orbit can remain. A beacon placed on an airless world can persist. A modified asteroid path could preserve evidence for far longer than the biological lifetime of the beings that created it. In that sense, the galaxy may be easier to read through leftovers than through live communication. That is a major change in mindset. It means the most useful evidence of intelligence may not be a conversation. It may be an object. And if you're thinking about long-term preservation, one place stands out immediately:
The Moon. The Moon is one of the best local archives in the solar system. It has no atmosphere, very little erosion, and very weak geological recycling compared with Earth. On Earth, objects get buried, weathered, melted, corroded, or pulled back into the planet through tectonic activity over long periods. Earth is active. It erases things. The Moon is much quieter. If something lands there and stays intact, it can remain for a very long time. That is why some scientists have pointed out that if extraterrestrial artifacts exist anywhere nearby, the Moon would be one of the most sensible places to look. That does not mean anything has been found. Nothing verified has. But from a preservation point of view, the Moon is an obvious candidate. A dead probe on Earth may vanish into geology. A dead probe on the Moon may just sit there. And this is what keeps the already on their way idea scientifically alive. Humans have not completed the relevant searches, not even close. A few decades of radio listening do not close the case on billions of years of possible technological activity. The search space is much larger than that. It includes local artifacts, orbital anomalies, unusual heat signatures, atmospheric chemistry, and many categories humans are only starting to study systematically now. So when people say, if something was out there, we would know already, that statement sounds stronger than it is. What we can really say is much more limited. We have searched some channels, especially radio, with growing sophistication, but we have not searched every channel. We have not exhaustively searched nearby space for artifacts. We have not fully examined every plausible archive site. We are still in the early phase of thinking about technosignatures in a broader way. That means a negative conclusion is weaker than people often assume. You cannot have high confidence that nothing technological has ever passed through, remained behind, or entered a stable niche if the search itself is still so incomplete. And that is the tension this section adds. If something is already on their way, if nothing is there, silence stops being reassuring. It may only mean the wrong search came first. Which leads to the next question. If something is actually coming, or already present, the first sign may not be a message at all. It may show up as an anomaly, something in the data that doesn't behave the way nature is supposed to behave. If something is coming, the first sign may not be a message. It may be a problem in the data. A lot of people still expect first contact to look clean and obvious, a signal, a pattern, a transmission that clearly looks artificial the moment it appears. But real science usually doesn't work like that. New things often show up first as a mismatch, something small that refuses to fit the model. So if an alien probe ever enters the picture, the first clue may be much less dramatic. It could be an object with an odd trajectory. It could be a small acceleration that doesn't match normal outgassing. It could be an unexpected reflectivity pattern. It could be a heat signature that doesn't match the material you think it is made of. In science, discovery often begins with residuals, the leftover gap between what the equations predict and what the measurements actually show. That is important because it changes the way first contact might really happen. It may begin with confusion, not certainty. Then there's the question of materials, because light can reveal a lot more than people think. Astronomers use spectroscopy to identify what distant objects are made of. Minerals, ices, metals, organics, and gases all interact with light in different ways. They absorb and emit different wavelengths. That means an object can leave a chemical and structural fingerprint in the data. If something artificial is out there, it might do the same. Highly refined metals, layered engineered surfaces, unusual coatings, or materials designed to manage heat in specific ways could stand out from normal natural objects. Not in a theatrical way, not in a way that immediately spells out alien, but in a statistical way. That may be how the first real clue appears, not as one impossible object that convinces everyone instantly, but as something that sits outside the normal distribution and keeps refusing to fit. And then there's the hardest category for nature to fake: motion. Nature can produce a huge range of strange shapes. It can produce odd rotations, weird fractures, irregular surfaces, and unexpected brightness changes. But motion is more constrained. If an object changes trajectory in a way that cannot be explained by gravity, radiation pressure, outgassing, collisions, or some overlooked natural force, the stakes rise very quickly. That is why unexplained accelerations get so much attention. Most of the time, they turn out to be bad measurements, incomplete modeling, or some natural process that was missed at first. That is exactly how science should work. You try to eliminate ordinary explanations first. But if one case survives all of that, then it stops being just an anomaly. At that point, you are no longer dealing with a curiosity. You're dealing with behavior that suggests control, and control implies intent. That is a very different level of seriousness. A weird shape can be geology. A weird path is harder to dismiss. And the real probe may choose to make that even harder by staying quiet on purpose. If the mission is observational, broadcasting may be the last thing it wants to do. Emissions reveal too much. They reveal where the object is, how much power it has, maybe even something about how it is built. A quiet probe is safer. It can rely on passive sensing, just watching, recording, and waiting. That means humans might detect it visually, thermally, or dynamically before hearing anything from it at all. You might see its motion before you ever see a message. You might detect its heat before it transmits a single bit. That flips the normal first contact script upside down. The first thing humans notice may not be language. It may be behavior. And the strange thing is, modern astronomy is actually built to find this kind of problem. Today's sky surveys generate enormous amounts of data. Astronomers track moving objects, near-Earth objects, comets, asteroids, transients, variable stars, and all kinds of changing sources at scales that would have been impossible not long ago. In one sense, that is good news. Humans are better than ever at spotting odd things. But there is also a downside. The data volume is so huge that rare signals can get buried, ignored, or misclassified. An unusual object may not fail because it was invisible. It may fail because it got sorted into the wrong category by an automated system, or because there were too many false positives around it. So if something artificial is moving quietly through the solar system, the discovery may not come from one scientist staring through a telescope and instantly understanding everything. It may come from a survey pipeline, or a machine learning filter, or a statistical alert that says one object out of a million is behaving differently from the rest. That is how the first real shock may enter the record. Not with certainty, not with a global announcement, but with a strange paper, a disputed anomaly, a weird spectrum, a small unexplained push, a controversial interpretation, and a growing number of people realizing the natural explanation is getting weaker instead of stronger. And that is what makes this scenario more believable, not less. It fits how science usually encounters the unknown. First the anomaly, then the argument, then the deeper investigation, and only later, maybe much later, the meaning. So the tension keeps rising. If something is coming, humans may not hear it first. Humans may notice that one object in the data does not act like a rock, does not act like a comet, does not act like anything the models expect. And once you accept that possibility, the next question becomes unavoidable. Why would any civilization send probes toward places like Earth in the first place? Because once you stop thinking in terms of invasion stories, the motives become more realistic, and in some ways, more unsettling. There are real reasons a civilization would send probes toward a world like Earth, and none of those reasons need to involve invasion. A lot of people jump straight to the most dramatic motive: conquest, attack, takeover. But that is not the most realistic reason at all. Science by itself is already enough. A planet like Earth is not just another rock. It has liquid oceans, a long climate history, an oxygen-rich atmosphere, active geology, weather, seasons, and the biosphere that has been evolving for billions of years. From a scientific point of view, that's an extraordinary target. Humanity would absolutely send probes to another living world if it had the ability. Humans already send machines across the solar system just to study places that are far less biologically interesting than Earth. So there's no good reason to assume an advanced civilization would be less curious than we are. That is the first major correction. You do not need hostile motives to make an alien probe mission make sense. Science by itself is already enough. Then the logic gets stronger if living worlds are rare. The galaxy may contain huge numbers of planets, but that doesn't automatically mean life is common. Planets can be abundant while actual biospheres remain rare.
If the origin of life is difficult, then every living planet becomes valuable. If complex multicellular life is rare, the value goes up even more. And if technological life is rare, then a planet like Earth becomes a very important observation target. Scarcity changes the calculation. A civilization may have little reason to visit endless barren rocks if what it really wants is data about worlds where chemistry turned into biology, and biology turned into intelligence. That means Earth may not be interesting because it's rich in ordinary matter. It may be interesting because it crossed multiple rare thresholds. And once a world crosses the next threshold, technology, the interest could increase sharply. A civilization might monitor young technological species for several reasons. Science is one reason, risk assessment is another, long-term cataloging is another. If radio leakage, atmospheric pollution, large-scale energy use, or industrial chemicals reveal that a biosphere just produced technology, that may stand out as a major development, not because it's automatically dangerous, but because it's important. A world that only hosted microbes is one category. A world that now hosts a technological species is a very different category.
That does not require paranoia or malice. It just means Earth could have become a higher priority target recently, even if it had already been known as a living planet for a very long time. Now compare that to the resource argument, because this is where a lot of people get the priorities wrong. Humans often assume aliens would come for water, metals, or energy, but on an interstellar scale, those are not the rarest things. Hydrogen is everywhere. Asteroids contain metals. Icy bodies are common. Stars provide huge amounts of energy. Raw material is widely available across a planetary system. Information is harder to find. Life is harder to find. Intelligence may be harder still. That shifts the whole logic of an interstellar mission. Earth is not especially important because it contains iron or water. There are easier places to get those. Earth is important because it contains a billion-year biosphere and a civilization that has just begun to observe the universe back. That makes information a more plausible motive than extraction. The real prize may be knowledge. And that changes what the mission would probably look like. If a probe is coming, the most realistic profile is not some theatrical public arrival. It is not landing in front of cameras. It is not a giant declaration. A serious observational mission would likely stay at a distance first. It might orbit. It might map the system. It might sample dust, comets, or the outer planets. It might study Earth's atmosphere remotely. It might monitor radio leakage, radar, and other signs of activity. It might relay information home, or if the civilization uses long-term autonomous strategies, it might build local infrastructure or replicate in some limited way. That kind of mission is much more plausible than the dramatic version people usually imagine. And that is exactly why it is more unsettling. The most realistic extraterrestrial mission is also the one humans are least likely to notice quickly. It does not need to be loud. It does not need to land. It does not need to intervene. It can learn a great deal while staying quiet. In fact, if its goal is information, staying quiet may be the best strategy. So this section adds a very important point. There are strong reasons to send probes toward habitable worlds, and those reasons do not depend on fantasy motives. Science is enough. The rarity of life is enough. The emergence of technology is enough. Information is valuable enough. And the most realistic mission profile would be observational, careful, and easy to miss at first. Which leads to the next stage of the argument. This way of thinking is not even purely about aliens anymore, because humanity is already moving in the same direction. In a primitive form, humans are already becoming the kind of species that sends machines outward to inspect distant worlds. Humanity is already starting to behave the way you're worried aliens might behave. That is what makes this idea hard to dismiss. It is not only speculation about some unknown civilization, it is also a projection of a pattern that humans have already begun. Humans have sent probes beyond the planets. The Voyager spacecraft are still moving outward and now travel through interstellar space. They are slow, they are fragile, and they were not sent toward known inhabited worlds. But the important point is conceptual. A technological species on a rocky planet has already started placing artifacts into the wider galaxy. The first step has already happened. That matters because it breaks a psychological barrier. Interstellar outreach is no longer an impossible category. Humans have already entered it in primitive form, and the next step is already visible too. Human astronomy is moving from simple exoplanet discovery into deeper characterization. It is no longer enough to just know a planet exists. Scientists now want to know what its atmosphere contains, whether it may have liquid water, whether it shows biosignatures, and eventually whether it shows technosignatures. Future observatories are being designed around exactly these questions. So once humans identify a truly interesting nearby world, one that might be alive or even just highly habitable, the next step becomes very easy to predict. Humans will want to send something there. That means the logic behind alien probe missions is not strange at all. It's the same logic humans are already developing for themselves. And this is where projects like Breakthrough Starshot become important. Not because they prove humans can do it today, but because they shrink the distance between science fiction and engineering. The basic idea is to use powerful lasers to push tiny light sail probes to around 20% of light speed, about 60,000 kilometers per second, or roughly 37,000 miles per second. The technical challenges are enormous. You need extreme precision in the beam. You need sail materials that can survive the acceleration. You need accurate targeting over light years. You need some way for a tiny payload to send data back. And you need to think seriously about dust impacts at very high speed. But the point is that this is not just random fantasy. It is studied seriously enough that it belongs in real scientific discussion. And once that happens, the whole argument changes again. If humans can sketch even the early version of interstellar probes so soon after inventing powered flight, then an older civilization could have developed much more advanced versions long ago. That is why the strongest argument is not that interstellar missions are easy. They are not. The strongest argument is that they are convergent ideas. Different motivations all point in the same direction. Curiosity points there, survival points there, prestige points there, redundancy points there. Exploration points there. Scientific ambition points there. Once a species becomes technological enough, outward probes become a very natural long-term project. That is what makes the alien psychology here less exotic than people assume. You are not inventing some bizarre motive that only non-human minds would have. You are taking a normal technological impulse and extending it over more time, more resources, and more capability. If humans can think this way within roughly a century of flight and a few decades of serious exoplanet science, then a civilization with a far older technological base may have turned that same impulse into a mature system long ago. And that leads to the final inversion in this section. Humans like to think they are standing at the beginning of cosmic exploration, as if the story starts here. But maybe humans are only at the beginning of awareness. Maybe the galaxy already contains artifacts sent outward by many civilizations, and humans are simply late in recognizing that this is what technological species eventually do. That changes the emotional balance of the whole subject. The disturbing part is not only that aliens might already be on their way to Earth. The disturbing part is that the behavior itself may be normal. It may be one of the standard outcomes of becoming advanced enough to study the universe in detail. In that case, humans are not looking at something absurd or uniquely alien. Humans are looking at a future version of their own behavior. So the idea keeps getting more grounded, not less. Humans already send machines outward. Humans already plan to inspect exoplanets more deeply. Humans already study ways to send tiny probes between stars. Humans already have motives that make those missions attractive. The mature version of this behavior may just be what older civilizations do as a matter of course. And once you see that, the final section becomes even more unsettling, because the most disturbing possibility is not a dramatic invasion or an impossible attack. It is something much quieter, much slower, and much more scientifically plausible than people are comfortable admitting. The most disturbing possibility is not invasion. It is that arrival could be quiet enough to look normal at first. Movies trained people to expect the wrong thing. They expect giant ships, obvious intent, impossible movement, instant communication, and some clear moment where everyone knows history has changed. But real astrophysics points in the opposite direction. A realistic arrival would probably be faint,
cold, distant, and hard to interpret. It might look like a dim object in an unusual orbit. It might look like a weak heat source near a useful gravitational location. It might look like a slow machine entering the outer solar system after traveling silently for hundreds or thousands of years. Nothing about that would have to look dramatic at first, and that is exactly why it is more believable, not less. That is the first thing that makes this idea unsettling. The realistic version is subtle. And if a probe were cautious, the outer solar system would be the obvious place to begin. It would not rush toward Earth. It would not immediately move into the inner planets where human observation is much stronger. A careful system would first assess the solar system from the outside. The Kuiper Belt and distant solar orbits make a lot of sense for that. This region starts beyond Neptune, beyond roughly 30 astronomical units, about 4.5 billion kilometers, or roughly 37,000 miles beyond the Sun, and extends much further outward. Sunlight is weak there. Temperatures are very low. Human monitoring is much thinner than it is near Earth. For an incoming machine, that is a very useful reconnaissance zone. It gives distance, cover, and time. That matters because it means an arrival may not begin near Earth at all. It may begin where humans are not watching closely enough. Then there is the communication problem, and this changes the mission design even more. If a civilization launched something from dozens or hundreds of light years away, it cannot run that mission like a drone with real-time control. Messages take too long. Updates from home would be delayed by years, decades, or more. So the probe would almost certainly need its own decision-making ability. It would need to choose what to observe, when to move, when to stay quiet, when to transmit, and possibly when to avoid detection. The farther away the origin is, the more autonomy the craft needs. That means a real alien mission would probably not just be a machine carrying sensors. It would be a machine carrying judgment. And that leads to one of the most important points in the whole script. If something like this entered our data, humans might misread it at first as an ordinary scientific anomaly. It might not enter the record as alien contact. It might enter as a weird object, an odd orbit, a strange light curve, an unexplained thermal pattern, a controversial acceleration, or a spectrum that does not fit expectations. It could become a technical paper before it becomes a public revelation. The measurements would arrive first. The meaning would come later. That gap matters a lot because during that period, scientists would argue, papers would be challenged, models would be revised, and ordinary explanations would be tested again and again. That is exactly how science should work. But if the object were actually artificial, then while humans were still debating what it was, it could still be carrying out its mission. That is a much more realistic version of first contact than the usual one. Not a clear announcement, but a long argument over whether something in the data is behaving too strangely to be natural. And that is what makes this idea scientifically dangerous. Not dangerous in the sense of an immediate attack, dangerous because it breaks a comfortable assumption. It shows that the universe does not need impossible technology to produce a result that feels shocking. It only needs deep time, huge distances, and patient engineering. Once you accept that, the idea that aliens could already be on their way stops sounding like pure fantasy. It becomes a real, unresolved possibility that fits inside known physics. That is the part people resist most. They want the idea to fail because it sounds too big, too dramatic, too strange. But the more realistic version is not dramatic in that way. It is quiet. It is slow. It is based on things the universe already allows. It does not require miracles. It only requires that some civilization started earlier, planned farther ahead, and treated centuries the way humans treat years. And once you see that clearly, the final step becomes unavoidable. Science still cannot say aliens are definitely coming to Earth. There is no confirmed probe, no verified message, no authenticated artifact that proves an extraterrestrial mission is inbound or already here. Anyone speaking with certainty goes beyond what the evidence allows. But the opposite kind of certainty is also a mistake. Science can say something narrower and in some ways more serious. The idea is physically plausible.
The galaxy is old enough, large enough, and full of planets that interstellar missions do not need to be treated like fantasy by default. That is the honest conclusion. Not proof, not certainty, but plausibility inside known physics. And the reason that plausibility matters is that it's built out of many separate facts that all point in the same direction. Humans know planets are common. Humans know rocky planets are common. Humans know some of those planets may be broadly habitable. Humans know many stars are much older than the sun. Humans know interstellar objects can move through the solar system. Humans know robotic exploration is easier than crewed exploration. Humans know autonomous systems make very long missions more realistic. Humans know the solar system contains stable and semi-stable locations where an artifact could remain for long periods. None of those facts by themselves proves that an alien mission is inbound, but taken together, they remove the lazy dismissal that this whole topic can be rejected just because it sounds extreme. That is an important difference. The argument is not, therefore aliens are definitely coming to Earth. The argument is, you no longer get to reject the possibility with one sentence. So the burden now shifts away from imagination and toward search. The next step is not to make stronger claims with weaker evidence. The next step is to look better. That means more all-sky surveys, better tracking of interstellar objects, more follow-up spectroscopy, more systematic searches for technosignatures, more attention to local places where artifacts could hide or persist. If something is out there, humans are not going to find it by arguing harder. Humans are going to find it by improving observation, improving classification, and testing anomalies more carefully. That is how this subject becomes scientific instead of just speculative. Better search, better filters, better data, better discipline. And this is also why the idea lands so hard psychologically. It changes your place in time. It forces you to stop thinking of humanity as the center of the story, sitting in a quiet universe waiting for something to begin. A young civilization like ours may have entered the story very late. If a mission was launched before humans existed, then history did not begin when humans started paying attention. The galaxy may have been running processes for millions of years before anyone on Earth could even ask the question. That is the deeper shock. It is not only about aliens, it's about timing. It's about realizing that human awareness may be very new compared to the age of the processes already unfolding around us. So here is the final line, stripped down to the core. Aliens do not need to break physics to reach Earth. They do not need warp drives. They do not need wormholes. They do not need impossible engines. They only need to have started earlier than us. And in a galaxy that has had billions of years to produce older worlds, older civilizations, and long-duration missions, that is not a ridiculous assumption. It may be one of the most reasonable ones. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.